All right, let's go, math people, let's go. Hey, if you want a free PDF, it's in Spanish and English in the description. And you can go ahead and download it, give it to your class, give it to your friends, do it yourself, whatever you want to do. Come on back and see how you did, all right? And I'll go over it with you. Okay, make sure you subscribe and like, and let's keep coming back. All right, tell your friends all around the world. Let's go. All right, we're going to solve systems of equations using the graphing method and so much more. All right, so this is kind of a plethora of different activities. Okay, let's start by graphing this line right here. This line has a y-intercept of -4, and it has a slope of up 3 over 1. So 1, 2, 3, 1, 1, 2, 3, 1. Then I'm going to go ahead and graph that line. With the graphing method, you got to be very, very accurate. So when you're in slope-intercept form, you first plot the y-intercept, that's the b, or then you apply the rate of change, the slope, from there. All right, so there's that line. Now I'm going to graph the other line. It's also in slope-intercept form. So I have a y-intercept of +3 and a slope of down 1 over 2. Oh, I love how that happens right there. When you apply the slope, you hit the other line. That makes it so nice. Okay, draw that line. Identify that point of intersection. That point of that point of intersection is right there. Looks like x is 2 and y is 2. You can check this solution pretty quickly if you go to your calculator and plug in that x value. So 3 times 2 minus 4. And notice how you get out a 2, which is the y value, right? So then y equals 2. So when I put in an x of 2, the output y is 2. Now I'm going to go to the other equation, input an x of 2, and I should get out a y value of 2. And I did. Let's go. That proves we're okay. All right, here's another equation in slope-intercept form. So this has a y-intercept of -5, and then a slope of up 3 over 4. I'm going to do it again. I'm going to draw that line. And please be accurate. In the graphing method, it's important you are accurate. So that point of intersection, if you're off just a little bit, it throws you off. So you got to really make sure you go through those lattice points. Lattice points are points where the grids intersect. Okay? All right, now I'm going to graph the other line. The other line is in standard form. So to find the x-intercept, let y be 0 and solve it for x. Divide both sides by 2, you get 3. Let y be 0. Let x be 0. Solve it for y. Notice there's no number in front of y, so that means it's a 1y. So y equals 6. So that's your y-intercept. When you let x be 0, that's when you'll find the y-intercept. Remember, these are ordered pairs, right? So that ordered pair is 0, 6. And that ordered pair is 3, 0. So when you find the x and y intercepts, you're finding 2 ordered pairs. Okay, I'm going to draw that line. The line gives me all of the solutions of that equation. And notice this, the one solution that works for both lines is that one right there. And that solution has an x value of 4 and a y value of -2. Okay, so 4, -2. All right, that's not bad. Now down here, we're just going to reiterate some skills that we learned before. All right, solving equations will never go away. Before you solve these equations, you want to simplify each side of the equal symbol. So there's my equal symbol. Notice on the left, I can apply the property called distribution. Now I'm going to solve this for x. So move your constant to the right. 3x equals 6. And then divide both sides by 3. So let's not forget these solving equation skills. It's very important. This is a one variable equation, so that is the only solution. These are two variable equations, so there's infinite solutions for each line. There's only one solution where they intersect, but notice the red line has infinite solutions. Every ordered pair on that line is a solution for that equation right there. Okay, now let's solve this one. This one has variables on both sides. Can I simplify this by distribution or combining like terms? No, because those are not like terms. Can I simplify the right-hand side of the equal symbol? Nope, not like terms, no distribution. So I'm going to go right into inverse operations. Subtract 3m. I like to put my variables on the left. Math is about real good habits now. Put that constant 8 on the right. Opposite or inverse operation of a plus is a minus. 4m equals negative 20. And then the inverse operation of multiplication is division. M equals negative 5. And you're done. All right, let's move on. Let's move on. Okay, more graphing. More graphing. Let's do this. Okay, number 4 says graph the line y equals x minus 2. Okay, it has a y-intercept of negative 2. That's in slope-intercept form and slope-intercept form. So slope-intercept form is y equals mx plus b. Notice the number in front of x is a 1 because it's 1x. As a fraction, it's 1 over 1. So from there, 1 over 1, 1 over 1, and you just keep going in that pattern. There's that line right there. This has a y-intercept of 0. All right, so I'm going to plot my ordered pair where y equals 0. Then I'm going to go up 3 over 2, up 3 over 2. I'm going to draw that line. This is going to be a tricky one. Really tricky. So let's make sure we're accurate again. Okay, it looks like our point of intersection is right there at negative 4, negative 6. All right, so before I move on, I'm going to check that. Okay, because when you get off a little bit, it throws your line off a little bit. So I'm going to go over here, and I'm going to check this answer. I'm going to go, instead of x, I'm going to put negative 4 minus 2. Ooh, I get out of negative 6. That's a good sign. I'll do 3 divided by 2 times the x value, and I should get out of negative 6 there as well. Ooh, and I do. Let's go. Good graphing. Okay, this is also in slope-intercept form. So y equals mx plus b. There's my slope. There's my y-intercept. So 5. Down 2 over 5. Down 2 over 5. Draw that line. Make sure it's accurate, please. Get those lattice points. Okay, there it is. And drive it all the way through. Okay, now I'm going to graph the other line. The other line is in standard form. Standard form is ax plus by equals c. So when I'm in that form, I find the x and the y-intercept. X-intercept is when you let y be 0 and solve for x. Negative 10 divided by 2 is negative 5. That is my x-intercept. My y-intercept is when you let x be 0 and divide negative 10 by 5. That's negative 2. Oh, look at this graph. Okay, okay, we've seen this before. We have seen this before. This has no solution. These lines are what we call parallel. They're the same distance apart always. They will never get closer than that. So they will never intersect. So that means there's no x and y that will ever make this true. So I'm going to say no solution. Another way people say it is no point of intersection, and that's fine. Just some way of saying there is no x and y where this is true. All right, we're going to go do some little function reminder here. Notice this is my g function, right? This is my h function. That's the name. And this is my f function. So I want to refer to them by names. G, H, and F. How you doing today? This says go to the f function and input a 2 in the rule. This is the rule. I'm going to input a 2 where I see an x. So notice it's an exponent. And then I'm going to put it in my calculator. I'm just going to simplify that. So do 4 exponent of 2 minus 9. And I get 7. So that means the f function with an input of 2 has an output of 7. That's done. Okay, notice here, h of negative 3. So I'm going to find that h function. I'm going to go to the rule, and I'm going to put in a negative 3 everywhere I see an input variable x. So I'm going to put a negative 3 there, and I'm going to put a negative 3 there. I'm going to let my calculator do the walk-in. So I have negative 3 squared minus 7 times negative 3. And I get 30. So that means the h function with an input of negative 3 has an output of 30. Right? Name input equals output. Okay, now notice this. Name input equals output. That is the output. So I'm going to go to my g function. And this is my output. G of x is my output. G of x equals negative 8. So all of this comes out, and negative 8 goes in. Your goal is to solve that for x. So I'm going to subtract 4. Negative 12 equals negative 3x. Divide both sides by negative 3. It's okay that my variable's on the right. That's okay. That's okay. I still do inverse operations to try to figure out what 1x equals. And I write 4 equals x, but I never write my final answer like that. It's always the variable equals. Boom. And we're done. Okay. Simplify means perform as many operations as possible. This is distribution. So negative 5 times 2 is negative 10, category x. Negative times a positive is a negative. 5 times 7 is 35. That's done, because these are not like terms, so you cannot subtract them. Okay, this is an expression, not an equation, because there's no equal symbol. So I'm just going to combine like terms. Notice how when I highlight like terms, I highlight them in the same color, and I highlight the operation that's in front of them. Very, very important. All right, so all my like terms are in the same color. Alphabetical order, so 2 minus 4 is negative 2. That's my new count, and the category is x. Now I'm going to do my y's, because it goes x, y, constant. This is a negative 3. So if I put this in my calculator, I'm putting it in as a negative 3. I know it says minus 3, but because it's the first term I'm putting in my calculator, I have to do it like that. And I get out a 2. So that's a plus 2, because it was a positive number, category y. And then 9, positive 9, minus 8 is plus 1. That is my final answer. So distribution and combining like terms. Very important properties. You will always use them in your math classes. Okay, let's keep going. Let's keep going. Problem number 8. Uh-oh. Some words now. Some words. My dog Hobbs was 1 pound at birth. I'm going to highlight that because that's important. And gained weight at a rate of 2 pounds per month. All right, looks like we have a rate and an initial value. That's y equals mx plus b. My friend's dog Penny was 6 pounds at birth. Okay, there's that initial weight. And gained weight at a rate of 1 pound per month. Okay, let's write functions that models Hobbs. I'm going to write that as h of x. All right, so this is the weight of Hobbs after so many months. The rate of change is 2, so 2 pounds times every month Hobbs is alive after he was born, plus Hobbs' initial weight, pardon me. Penny I'm going to call P of X. Penny was initially 6 pounds at birth. Woo, she was a big girl. And sorry, 6 pounds was your constant, right? That's your initial value. And gain weight at a rate of 1 pound per month. Okay, there's your functions. Let's graph them. Okay, notice Hobbs. Hobbs started at 1 and then go up 2 over 1, up 2 over 1, and we just keep that pattern every month for as long as this model is good. And then I graph it. Okay? And the goal is to find out how many months did it take for Penny and Hobbs to get to be the same weight. I'm going to highlight this in Hobbs' color so we know that that's Hobbs. Hobbs was yellow. All right, now I'm going to graph Penny. Penny started off at 6 pounds and gained weight at 1 pound per month. Okay. Looks like we found a point of intersection right there. Looks like that's our point of intersection. Let's keep going. Let's graph it correctly and nicely. Let's finish our work. Okay. There's that. Notice Penny was orange. So that represents Penny's graph. Okay, the point of intersection looks like it's 5, 11. Okay, so graph each function, identify how many months it will take for the dogs to weigh the same and how much will they weigh. Okay, so look at the ordered pair. The input X and the output Y. The input is months. So that means after 5 months, right, the output is the weight. Each dog will weigh 11 pounds. That's it. All right, so you have to have meaning on these X and Y's now. If you wanted to check it, which is always a good idea, you can. So go to Hobbs, put in a 5 for your X. You get out 11, that's a good sign. Go to Penny, put in a 5 for your X. Get out 11, boom, we nailed it. All right? Not bad. Okay, here we go. Today, Leo planted a tree that was 12 feet tall. Okay, so Leo's tree started off at 12 feet tall and grows at a rate of 1 foot per year. Okay, so that's the rate at which Leo's tree grows. On the same day, Bianca planted a tree that was 3 feet tall. That's the initial height. And grows at a rate of 2 feet per year. And that's the rate of change. So it looks like we have Leo. So I'm going to call it L of X for Leo equals, there's my rate of change. So 1x, because that's my input variable I chose, plus 12. And Bianca, I'm going to call that B of X. Well, notice Bianca has a rate of 2 feet per year. That's how fast Bianca's tree grows. And started off at 3 feet. Okay, let's graph it. So Leo started at 12 right here. Looks like they went up by increments of 3. Be careful here, because when I go up 1 over 1, okay, it looks like they're both increments of 3, so we're okay. So if I go up 3 over 3, up 3 over 3, then we're going to be okay. All right, I really have to be careful about my increments on this one and how that guides my applying of the slope. Okay, that is Leo's tree, so I'm going to do that in yellow. Bianca's tree started off at 3 feet, so way down here, but grows at 2 feet per year. So I'm going to go up 2 over 1, up 2 over 1. Ooh, there it is right there. All right, there it is right there. Notice my increments were by 3s. So I really went up 6 over 3, but isn't 6 divided by 3 2? So it's equivalent to 2 over 1. All right, and that is Bianca. Bianca's tree is growing much faster than Leo's. Okay, now we have a point of intersection right there. That looks like 9, 21. Okay, so the x value is years that the trees have been growing, and the y value is the height of those trees after x years. So 9 years after they planted them, they were both 21 feet tall. Okay, so after 9 years, comma, both trees were 21 feet tall. That's it. That's it, my people. All right, awesome. Good work. Let's keep going. Last page. Ooh, I love these problems. Low rocket. Let's go, rocket. Okay, refer to the given graph. A rocket was launched from a hill. Okay. Notice it was launched on a hill that was this high off the ground. Okay. Because that's the initial point where the rocket took off and landed in the valley below. So this is where it landed. That is elevation 0. And I know because the y value equals 0. All right? And notice the distance from the launch place on top of the little hill to where it landed was 18.1. Okay. So it looks like that's meters. Okay. And this is time in seconds. So that's, x is time in seconds. And y is meters, distance off the valley floor, right? Elevation off the valley floor. Okay, let's do it. So x is time rocket is in the air in seconds. That's the x-axis. The y-axis is height off the valley floor in meters. Okay, highlight any increasing intervals in yellow. Okay, increasing means it goes up from left to right. Boom, 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 boom. Yeah. And any decreasing intervals in blue. Blue means it goes down from left to right. Ticka, 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 ticka. Right there. Okay. How high was the rocket after 15.1 seconds? Well, x is the time. So that's 15.1 seconds. So it looks like 20 meters. So 20 meters. Please use unit of measurement on these problems. How high was the rocket after 15 point? I just answered that. How many seconds was the rocket descending for? Okay, so notice it started descending right here at 8 seconds, and it landed at 18.1 seconds. So if I do 18.1 minus 8, that gives me 10.1. So it was descending. It went to its highest point in 8 seconds, and then it took another 10.1 seconds for it to descend down to the ground. Let's make sure we use unit of measurement, please. Okay. E, what is the maximum x value? Well, the maximum x value is right here, 18.1 seconds. That's how long the rocket was in the air. What is the minimum x value? Well, the minimum x value is times 0, right? That's before the rocket launched. 0 seconds. What is the minimum? What is the maximum y value? Well, that's its highest point. Ooh, that rocket got to be 46.7 meters. That's huge. It's like 130 feet plus. So 46.7 meters. And then h, what was the minimum y value? Well, that's when it hit the ground. And it hit the ground at 0 meters. Because when it hit the ground, it's 0 meters off the ground. So 0 meters. I, is the graph linear or non-linear? Linear means it doesn't make any turns or curves, right? So that's definitely non-linear because it curves. So non-linear. What does the point R 18.1 equals 0 represent? Okay, so the name of the function that models this is R. The input value is 8.1, and the output value is 0. So that represents this point right here. Well, what does that point mean? That means after 18.1 seconds, the rocket, the rocket landed on the valley floor. On the valley floor. Or on the ground is fine. That's all, right? That represents the maximum time it was in the air, and 0 represents the moment it hit the ground. All right, kiddos, good work, good work. Have a great day, stay strong. Don't forget to subscribe and like. Woo!